Hi there. Well, in this video we're going to look at really two definitions here of what it means to be continuous. And in the first definition here we have what it means to be continuous on an open interval, which we've already looked at in a prior video, and we're going to extend that to a function that is continuous on a closed interval. And I just realized that there should be a D there. I misspelled that, but that should read on a closed interval AB. Okay, so real quickly, a function is continuous on an open interval if it's continuous at each point on the interval. Okay, what does that look like graphically? Well, if I have a function and I'm interested in a particular interval from A to B, okay, and I don't care about what happens at A or B, I just care about what happens in between A or B. If I want a function that is continuous on this open interval, then it might look something like this. Maybe I have a little hole here, and maybe it comes up here and then back down here, and maybe another little hole right here. Now this is a continuous function on the open interval. Okay, remember that an open interval doesn't include the endpoint, so I really don't care about what happens at A or at B. But you can see that if you consider any x in this interval right here, it's going to get mapped to this curve. And when you draw this curve, you don't have to pick up your pencil anywhere along the way. So this is going to be continuous on the open interval AB. Now, this would be, let me just write it here, continuous on AB. Okay, so let's go ahead and look at another example. And again, if we consider an open interval from A to B, well, what happens if we fill in a little hole? Okay, so it looks like the same graph, only this time we've defined where A went. Okay, we can still talk about this thing being continuous on this open interval if we want. Okay, so again, we can go ahead and say continuous on AB. Okay, so really, when is a function not continuous on an open interval? Well, it's not going to be continuous on an open interval AB if there's some kind of discontinuity within this interval. Okay, maybe there's a hole. Maybe there would be a hole right there. Okay, then it would not be continuous on the whole interval. Maybe there's an asymptote in here. Maybe there's a jump in the function. What do I mean by a jump? Okay, well, if we consider yet another one, here's an open interval AB, and maybe my function does something like this. Maybe there's a closed dot there and then an open circle here, and maybe this is linear from here on out. Okay, if I just look at this interval, now I know I've gone outside of the interval, but that's okay. I'm only interested in the interval. Well, we can see that we have a discontinuity here, so this is not continuous on the open interval AB. Okay, now what if we want to extend this idea of continuity on an open interval to continuity on a closed interval? Now remember, there should be a D here, a D. Okay, so what if we're interested in a closed interval AB? Well, there's just two other conditions that need to happen. Really, if you're going to be continuous on this closed interval, well, you better be continuous on the open interval. Okay, and because it's a closed interval, now the endpoints matter. Now we care about what is going on at A and what is going on at B. Okay, so in walks are one-sided limits, and you can see here that as we approach A, there's a plus sign here. I don't know if you can see that in the video or not, but this is the limit as x approaches A from the right of f of x equals f of A, and this says the limit as x approaches B from the right, let's see here, from the left, I'm sorry, of f of x, and that should equal f of B. Well, that might be confusing to you until you look at graphically what exactly that means. Well, let's consider another function on a closed interval this time. This time we care about where A is and we care about where B is. They're included in our interval. Okay, so let's go ahead and look at an example here. And I'm going to just do a pretty basic one. Okay, so here's an example. This function certainly looks continuous on the open interval. I didn't have to pick up my pencil at any time to sketch this graph. But more importantly, if we're interested in the closed interval now, if we look at the limit as x gets close to a from the right-hand side, what is my function doing? Well, my function is getting really close to f of a. So here, the limit as x approaches a from the right of f equals f of a, whatever that is. I don't know what that is. Here's f of a right here. Maybe it's 2. I don't know. Okay, and then likewise, if we go to b, if we approach b from the left-hand side, we can see that f is approaching f of b. Okay, in other words, the limit as x goes to b from the left-hand side, or from the negative direction of f of x, that indeed equals f of b. Okay, so this is an example. If this function right here were f, okay, just some random function, we could say f is continuous on the closed interval a to b. And the reason that is, once again, is because f is definitely continuous on the open interval a to b, and these two limit statements check out. Okay, let's look at an example of where maybe that won't happen. Excuse me. Okay, so consider the following graph. Let's look at the following. Maybe I have something like this. Maybe that's B, and maybe this is A. Actually, let's get rid of this right here, and let's just call that an open or a closed dot right there instead. We won't confuse it any more than it has to. Okay, here we go. So this certainly is continuous on the open interval a to b. As I travel in between a and b, not including the endpoints, as I travel in between them, I don't have to pick up my pen or pencil to sketch this graph. Okay, now if we look at the limits as we approach a from the right and b from the left, what are those limits? Well, we can see that as we approach a from the right-hand side, as I approach a from the right-hand side, that my function approaches what looks like f of a should be. Okay, but ask yourself, is a even in the domain of my function? And clearly it's not. A doesn't get mapped anywhere. Okay, so we would say the limit as x goes to a from the right of f, in this case, it does not equal f of a. How come? Because f of a doesn't even exist, so there's no use to even consider this limit if a is not even in the domain. So this would be an example of a function not being continuous on the closed interval ab. It's still continuous on the open interval ab, but just not the closed interval ab. So we may say something like f is continuous on the open interval AB. Okay? Well, let's look at one more example here. Okay, let's go ahead and have a function that maybe at A, sorry about that, it's messed up. maybe this is A right here, and this is B. Okay, and maybe we have this function that comes cruising through and is continuous, and maybe it does something like this. Okay, and I'm interested in the continuity of this function right here. Where is this thing continuous? Well, if you noticed how I drew it, I didn't ever pick up my pencil to sketch the graph of this thing. It is continuous, it looks like, everywhere. So you might be tempted to say this is continuous on the closed interval AB, which it is, but it turns out this thing is continuous everywhere. F is continuous everywhere. Now, a way to write everywhere is you could say the whole real number line from negative infinity to positive infinity. Okay, so there you go. In the next video, what we're going to do is we'll look at some more specific examples with some actual functions and discuss their continuity. We'll see you there.